Alright, so the last data structure that I'm going to touch on now briefly is going to be the tree. Trees, just like linked lists, the node within a tree also points to the next node. Now a tree, just like the tree that you know in the real world, it's a data structure in which a node may have at most two children on the left and on the right. Now the way that binary search tree works is that the left child uh, of a node contains a smaller value, whereas the right contains a greater value than the node value itself. So here's a small example of how it would work. This would be the root node. The parent node is after the root node. Then we have the child node, and then the last node after the child node is it's a leaf node. So the ones at the pretty much on the leaves. Let's say, for example, we receive the value 20. We then check to see do we have anything else in our tree, or this is the first value that we're receiving. If it is the first value, 20 then becomes the root node. Okay, so now 20 has become our root node. Later on, we received another value and we received 30. We then check to see is 20 the root node less or is it larger than the incoming data. In this case, 20, our root node, is less. It's 20, which means our incoming data is much more with greater value than our root node. So we're going to store it on the right. So then we now have a root and then we have a leaf node. We receive another value of 15 incoming data. So now we then say, okay, we receive 15. We compare that 15 with our root data, our root node. Our root node is 20, which means it's bigger than the incoming data. In this case, we then store it on our left. So we repeat that very same strategy throughout. We repeat that throughout. Hence we say that we can use recursion we can actually use recursion to continually evaluate to see when data is coming through. So if we are done with we received the 15, then the next value that is coming, perhaps we are going to receive 10. If we receive 10 is less than the root node, which is 20, then it goes on the left. And then is 10 less than now the 15 that we have, the yes is less than, it goes on the left. Then we have now a tree already starting to form, as you can see. So we continually do that. If we are to receive then a 40, we then say, is 40 bigger than 20? Yes, go on the right. Is 40 bigger than 30? Yes, go on the right. Then it stores on the right. But if we are receiving, for example, maybe let's say we received 27, we check if 27 is bigger than 20. Yes, it is, go on the right. But then is 27 bigger or smaller than 30? Well, it's smaller, then goes on the left, then it gets stored on the left. So that keeps on happening. Now what happens is that there is, if it's left unbalanced, a tree can be very long on one side and then it becomes an unbalanced tree. So to counterbalance that, we have algorithms embedded within our trees that then revises the structure in which our data is being stored. Let's look here, for example. Let's say here we have stored we have 20 on the left, 20 on the 15 on the left, 10 on the left, and then 5 on the left, and then an 8. As you can then see here that we have a height from the first level here that we're looking at is it's 2 from 15 we have 2, 1, 2, and then the second level here that I'm looking at is 3 from 15, which is 1, 2, 3, and then the last one that I'm looking at is 4, which is 1, 2, 3, 4. So now we have this side being very, very tall or very long. So now we using an algorithm, I'm not sure how to even pronounce it. Aldelsonversky Landis, pardon my pronunciation there. The name is quite complicated. We then revise the way that we are storing here. So we then look here. What do we have? The data that we have 10, 5, and 8. Now 8 moves up here, and then it then looks and say, okay, if 8 moves up here, we're now left with 10 and 5. It then stores 5 on the left because it's going to be less than 8, and then 10 is stored on the right. Okay, this was just a typo. Let me actually just correct that as we're working through it. Alright, so here we have a 10. Like that. Alright, let's see. So then it revises these 3. So it does that to keep it balanced. So what are the operations that we find in a tree? Well, the operations that we're going to find in a tree is to insert and then to traverse the tree to see all the items that are within the tree. For example, the smaller problem that we have to deal with is to check to see the value on the left and the value on the right and compare it with the parent or the root. And the way we can do that recursively. And what is our best case? Our best case is to check if there is space to add the node. And then here's an example of how I've implemented that. So I have a class which is the BST, the binary search tree. Then I have a class node within that class as well. This now class node, it basically has a constructor function that establishes the data as a variable, and then the left and the right, which is a none at the moment because they haven't been defined yet. Now in the BST class I have this insert function which calls this function here. Now if you see, I've used a recursion in here. So here's how it works. If data which is coming now is less than node.data, which is then the data that we have here in this node. So we're saying if it's less than if this data is less than that, we run through this function. So what is this function then doing? We then check to see if the left of our root node is none. If the left of our root node is none, we then assign the incoming data on the left. Otherwise, if it's not none, which means we are going to insert, we're going to recursively check again to see if, which means if it's not a none, there's something on there. Then we recursively check to see the value there. Then we also have another one that checks to see if the data is bigger than or equal to the data on our root node or on our parent node. And then we do exactly the same thing that we did here, except that we're doing it on the right, and we're calling this insert recursively to continually check rather than having to do it manually. So that's how it's working here. So in doing that, we then can simply add items to our tree. Now your task is to learn and figure out how to traverse the tree itself. Alright, so I'm going to leave you with this class here. Now you have to add another function that then you can implement the logic of traversing the class. Cheers.